Welcome to Lecture 3 of Computer Science 767. So in the last lecture, we've been talking about constraint satisfaction problem, where multiple agents representing the respective variables in the problem looking for legal assignments of the variables such that collectively satisfy the constraints as laid out by the problem. In many real-world applications, merely searching for a legal assignment is not enough, but rather people are interested in solutions that are optimal with respect to certain evaluation, and that will be a type of optimization problem. And just like constraint satisfaction problem, it's also possible for us to turn a classical optimization problem into a multi-agent setting to look at a decentralized version of optimization problem. So in this lecture, I'm going to introduce this paradigm using an example, namely the assignment problem, which is well studied and prevalent in the literature. So formally, how do I define an optimization problem? Just like the constraint satisfaction problem, it consists of a set of variables, V, and a set of values and the domain function defined for each variable. And then, just like in constraint satisfaction problem as well, the solutions are functions that assign the variables to values in the domain. But moreover, we have this evaluation function VAL, which maps solutions to a real value, and this value can represent some sort of score or cost. Right? So if it's score, then of course our goal is to maximize the evaluation, so maximize the score. And if it's regarded as a cost, then our goal is to minimize it. And there are, so since undergraduate level computer science, I think we have seen many different optimization problems. A pathfinding problem, which is the classical graph theoretical problem. We have seen in the past also minimal spanning tree problem, traveling salesperson problem, scheduling problem, and so on. All of these problems fall into the category of optimization. So a solution is optimal if the value for the solution is either maximized or minimized, depending on whether we see it as rewards or cost. And the task asks us to find such an optimal solution. And just like in CSP, the distributed version of this optimization problem will be to implement a multi-agent system that collectively the agent will be able to find a solution to the problem which is optimal. So not only we're going to discuss solutions to the assignment problem, but very importantly in this lecture, I would like to bring up a notion of basically economic theory can be utilized in the development of multi-agent system, because economics ultimately is a science that studies agent behavior as a relation between end and scarce mins, which have alternative uses, and it's a study that which focuses not just on a single individual, but on a society which contains multiple individuals. And this parallels the main assumption of multi-agent system, because where in economics it studies people, but in multi-agent system we study agents, but they are also assumed to be rational and self-interested, right? So and in the multi-agent system, the scarce resources can be achieved by allocating some sort of price system, and the agent's decisions can be made through a process which derives trade-offs between the scarce resources that they face. So in this way, economic theory provide a whole range of tools and mechanisms that can be utilized in the design of a multi-agent system, right? And in fact, this will be demonstrated in today's lecture through the assignment problem. So what is the assignment problem? Imagine we have a number of tasks, so there are n tasks, and each is allocated to an agent. And there's a reward which is given to the task. If the agent has certain value that's chosen for the corresponding variable, then there's a reward that's gained by this agent, right? So formally we have a set of agents, A1 up to AN, and we have a domain, and just for simplicity, we assume that the domain X is shared among all the agents, so that every agent is able to choose some value within the domain X. And what is a solution is basically a function that maps agents to the domain. And we also require that, because it's an assignment problem, we require that the different agents would be assigned to different values in the domain in a solution. So this means that you can think of it as a shop, right? So we have the agents A1, A2, A3 up to AN, and then we have the same number of items or commodities in the shop, X1, X2 up to Xn, and the commodity can only be given to one agent. It cannot be split among different agents. So eventually the agents wants to take some items. Everybody wants to have an item by themselves, and all the items want to be distributed to some agents, right? And what is the evaluation? So this depends on essentially a local reward function. So what is a local reward function is given an agent and an item. Suppose I assign this item to this agent. Then this assignment, just single assignment to this particular agent, would give me a reward. So you can think of this reward as the benefit or the utility that this agent receives by having this item, right? So it's a utility that this item gives to the agent. But of course, this is only local. But what we are interested in from a global point of view is an evaluation function that's defined on the solution, which assign to all the agents some item. So this evaluation would be the sum of the local rewards gained by all the agents. So that expresses the this formula, which is a sigma from I to 1, from I equals to 1 to n of all of the v's of AI with a given item SAI. Right? So a solution is optimal if the value of the solution is maximized, because here we're treating this evaluation as being a utility, and obviously we want to maximize utility in this sense. For example, if you look at this example below, we have three agents, A1, A2, A3, and we have three items, X1, X2, X3. And in this table, you may see that the reward, the local reward that's given to each agent by the item is indicated at the respective entry in this matrix. For example, A1 will get a utility of 2 if the agent receives X1. And we get a utility of 4 if receiving X2, and 0 from X3, and so on. Right? So all we have is this table as input, and we want to assign values to the agent. So assign A1, for example, X1, A2, for example, X2 assigned to A2, X3 assigned to A3. Then you can see that in total we got a total evaluation value as 9, because 2 plus 5 plus 2. So we can, of course, mathematically formulate this problem as a linear program. For those of you who know a bit of linear programming, we can define the variables y, I, j for every I and j which are in the range of 1 and n. And this value is equal to 1 if AI xj is selected. So this means that if the item xj is allocated to AI, then yij is 1. So this indicates that this holds, and 0 indicates that it doesn't hold. So you can this y value is just a Boolean variable. And then we want to maximize the total utility. So we want to maximize the sum for all of the ij's of the value v ai xj times yij. So you can think of if we assign xj to ai, then this yij would be 1, and therefore we add this local reward v ai xj into the sum. And if yij is equal to 0, this means that this xj is not given to ai, then we do not add this value to the sum. Right? So this is the objective function that we want to maximize, but we also need to require that the y values need to satisfy some constraint. For example, the sum of all of the j's from 1 to n of, the sum of all of the yij's is bounded by 1, so it cannot be bigger than 1. Right? This means that, and given that each of the yij is just an integer, this means that every agent can receive at most one item. And similarly, the next constraint, which says the sum for all of the I equals to 1 to n, yij is less or equal to 1. This means that every item is assigned to at most one person. And also yij is bounded between 0 and 1. This is just bounding the range of this y. And if we view this as an integer programming problem, then we can use the existing method of linear programming to solve this instance of the problem, and we'll be able to get a solution. Of course, this will correspond to a centralized solution for this problem. But if we really view each variable as an agent, and each agent acts autonomously, then like what I said, I'm going to apply an economic paradigm to solve the problem. And this means that I would want to implement a price system. So essentially, you can think of the scenario as agents going into a shop, and each agent wants to select one of the item, and they're willing to pay certain amount of money in exchange for the item and the utility that it brings. So under this paradigm, really allocating items to agent would be imagined as agents purchasing the corresponding items, and the profit for each agent so no longer is just utility, but no longer is the local award, because each agent need to essentially give up a certain amount of money. So the net profit, or here I define as the real utility of the agent, would be the local award of receiving the item minus the price that the agent paid for the item. Right? So VAI xj minus P of xj, that's U of AI xj. Right? And for example, if we have the prices for x1, so notice that the price is the same for all the agents, right? In this scenario. So if we fix the price of the item x1, x2, x3 as 2, 4, 1 respectively, and if we eventually have an outcome so that agent 1 purchased x1, agent 2 purchased x2, agent 3 purchased x3, then you can see the utility of the agent 1, 2, 3 are respectively 0, 1, 1. Then, of course, the total utility of the whole setup would be 2. Right? And so how do we use this price mechanism to find out an optimal assignment among the agents? Right? If we implement this market mechanism, then we will need to make certain assumptions about the setup of each agent. So we assume that each agent is self-interested. They desire to maximize their own utility. They do not care about the utility of the other agents or the global utility. And you can then naturally see that there's a disparity between the individual desire and the collective desire. So what's necessarily the best decision for an individual may not be the best decision for the whole group of agents. Right? So what is the connection between this individualistic optimal choices and the global optimal solution? That's really the crucial question here. Right? And imagine we have this setup, which I just described in the last example, where agent 1 receives x1, agent 2 receives x2, agent 3 receives x3. You can then see under the current price of the items, namely 2, 4, and 1, the item x1, in fact, is the best choice for A1 to obtain. Of course, x2 also gives the same utility for A1, but x3 gives a -1 utility. So A1 will be very happy to get either x1 or x2 because they give the same maximum utility. In this case, A1 gets x1. And then if you look at A2, A2 gets a utility of 1, and that also happens to be the maximum utility that A2 can get out of the 3 items. And similarly for A3, x3 is the item that give A3 the maximum utility. So in this sense, you can see that indeed every agent is getting their individual optimal outcome. Right? But is this outcome necessarily the global optimal solution? In this particular example, yes, because you would not be able to find any other assignments if you disregard the price. If you just look at the total reward that everybody receives, and you would not be able to find another assignment function which give you a higher reward. So this particular setting, indeed, the agents get their optimal solution. Right? The question is this setting universal? So can you actually generalize this to arbitrary situation? And is that under this setting, yes, indeed, the individualistic optimal choices, if you collect them together, if everybody are making their individualistic optimal choice, then we will guarantee global optimality. So really the invisible hand of the market is working in this problem. Right? And I'm going to formalize what I've said using a definition of equilibrium. So equilibria are studied in almost all the economic context. So it's an outcome in which all the people are individually making some sort of optimal decisions for themselves, and then the society reaches a certain stable point. Right, that would be an outcome, and in this case, we're going to define competitive equilibrium. So a solution paired up with a price function P, which is defined over all the items, are in competitive equilibrium, and for every agent AI, the utility that AI receives under the current solution would be bigger than the utility that AI would receive had it received any other item, right? So or it's not smaller than that at least, right? So the U of AI of SAI would be bigger or equal to U of AI xj for any xj in capital X, right? And that's competitive equilibrium. This is the state where the individuals are making their separate optimal choices, right? And we can, just for simplicity of notation, represent the solution S as a vector, and that will be a vector representing the item that's given to the agents in the fixed sequence of A1, A2, A3. So X1, X2, X3 represents that A1 gets X1, A2 gets X2, A3 gets X3, and the price is also represented as a vector of price for each of the items. And here in this case that we have a competitive equilibrium in this example. So, like what I said, the equilibrium captures our prediction of the outcome of the multi-agent system, or the market that's formed by the agents. And when we regard the agents as what we call homo economicus, and this means that they make rational decisions based on their consideration of benefits and costs. And once we define a type of equilibrium, we normally would like to basically tackle three questions. The first one is, does the equilibrium always exist? And there are notions of equilibrium that in some cases will never be able to reach. So in this sense, it doesn't exist. So in this case, does it exist? Optimality problem, does the equilibrium guarantee global optimality? Right? And computational problem, because we are computer scientists and we want to implement not just a market for humans, but really a multi-agent system where the agents are artificial agents that function powered by some computer programs. So we need to care about the computation complexity issue. So how can we design efficient algorithm to find the equilibrium? So the first question has a positive answer. For any optimal solution, there exists a price such that together with the price, this optimal solution S will satisfy the competitive equilibrium condition. This can be quite intuitive to see, but I'm not going to prove it. But basically it says that if you have any optimal solution, this is a solution under certain arrangement of under certain setup of the price of the items. This will be a solution which is the best for everybody, right? So there is a competitive equilibrium always, and the optimality theorem is really the converse of the existence theorem. It says that suppose we have a solution and a price, and they are indeed competitive equilibrium, then that solution must be a globally optimal assignment, right? So the previous existence says that if you have a globally optimal solution, which always there is one, then that corresponds to a competitive equilibrium under certain price. And the next direction, which is really the optimality, says that if you have a solution, a price, which are in competitive equilibrium, then of course S will be a globally optimal assignment. How do you prove this fact? It can be done using a number of steps that are quite intuitive. You just need to connect them together. The global rewards of the optimal assignment can be expressed by this A star here and the equation which I gave on the slide. The global reward of the function of the assignment S is represented as D, which is a sum of I equals to 1 to n of all of the VAI SAIs, and you can see that because an A star is the maximum among all of the possible solutions, so of course you have D less or equal to A star, and what we want to show is the other direction, that A star is also less or equal to D, and this can be done by a sequence of derivation which I laid out on the slide. I'm not going to read it out to you, but you're encouraged to work it out yourself. So the next question would be the computation problem, which asks for an algorithm that finds the competitive equilibrium. Right? Here, when we talk about multi-agent system, because we're borrowing a economical mechanism, a very convenient way to achieve competitive equilibrium, which is what we want, is through essentially a simulation of the market mechanism that enable the emergence of the competitive equilibrium in real life. So if we imagine each of the agents is just a human being who is participating in the market, and according to the analysis of economics, if they exercise certain rational decision making, they will be able to arrive eventually at competitive equilibrium. And one of the mechanisms that humans use to determine price of item and the allocation of the items to the market participants is auction. And so we could, for example, design a set of procedures which mimic the procedure of auctions in real life, and we would like all the agents to follow this procedure, and eventually, hopefully, it will arrive at the competitive equilibrium that we want. Right? So what we'll do is want to study how do we implement an auction. An auction is a market institution with an explicit set of rules to determine resource allocation and price on the basis of bids from the market participants. Right? So in order to implement an auction, we will need to design what we call bidding rules and agent bidding policies. Right? And there are lots of different possible bidding rules in the world in terms of deciding on the price of certain item. For example, we got the English open cry auction, which is similar like to buying houses in Auckland, where buyers gather together and then they shout out bids, and then they increase the bids one by one. Eventually no one want to shout out another bid, then the winner is the one that has the highest bid. The other type of bidding system is, for example, the Dutch auction, where in their flower market, the bids goes down instead of going up. Right? So there's a whole literature of auctions and computation aspects of auctions out there, but today I'm not going to discuss that. I'm going to implement a very simple structure for a bidding mechanism for solving the assignment problem. So the general structure of the auction works as follows. The agent sends bids to the mechanism to indicate their willingness to exchange goods. So this bid will be essentially just saying, I would like to participate and how much money I would like to put on a certain item if I can get it. Right? The auction may post price quotes to provide a summarized information about the status of the price determination process. So the auctioneer, for example, would say, okay, right now for this item, agent 1 is leading, with this price, and for this other item, agent 2 is leading with that price, and so on. So all of this information is announced, and then the agents just iteratively send out higher bids in order to take the item that they think is the best. So this basically mechanism repeats itself until for every item no one is willing to send out another bid. At this point we've decided the price as being fixed, and the item will be allocated to the winner of those items. As a simple example, let's consider this case. We have this bidder who's looking at two cars, car A and car B, and imagine we have an ongoing auction where car A is currently valued at $20,000 and the car B is evaluated at $28,000. And imagine that for this agent, there is this local reward that the agent will get out of these two cars, and the agent know well about the local reward. So for car A, if she gets it, she'll get a reward of 22,000, sort of satisfying score, right? And compared with 20,000, this is higher than the 20,000, right? And for out of car B, the agent will get $29,000 as a reward. So if you think about it, the car A will give the agent a net utility of $2,000, and car B will give the agent a net utility of $1,000. So the question is, which car should she bid on? Very naturally, she should bid on car A because that gives a higher utility. So the next question is, how much should she bid on car A? Of course, the current price is $20,000. So in order to get the car, she needs to bid a higher price. Right? And she would really want to have this car. So she wants to bid at the highest possible price that she can in order to eliminate the competitors. And there are some competitors that are not shown in this picture, right? So she would, the highest value that she's happy to bid on the car will be $21,000 instead of $22,000. Why? Because if she bid any value more than $21,000, then the utility that she will get is not as high as the utility the car B gives her. So she would not be happy to bid at any price higher than $21,000. The highest would be $21,000. Right? So the reasonable action for her to do is to bid the car A with $21,000. Okay. So suppose now she sent out this bid, says, okay, I want to bid car A at $21,000, and there's a competitor who's sitting somewhere else, and the competitor look at the price of the cars and think, well, I think car A is worth $22,000. I think car B is worth $30,000. So in this case, very naturally, the second agent would bid on car B, and just using the same logic as for the first agent, the second agent will think, well, the price that I'm willing to pay for car B is $29,000 because that's the maximum that he's willing to pay, which make car B's utility not lower than the utility from car A, right? So he will bid at $29,000, and now suppose it's a third person who comes and look at the price of these two cars, which so if you look at the two cars, the car A will give the third person $22,000 of utility, and car B will give the third person $29,500, and therefore, very naturally, the third person would like to bid on car A at a price of $21,500, and then because it's an iterative procedure, the first agent will reevaluate, and because then car A is no longer held by her, so she will need to make a decision on whether she would like to send out another bid. Of course, car A's current price is still lower than her utility, and therefore she will say, well, I could of course bid on car A at $22,000, right? And at that moment, the third person will look at the situation thinking, well, car B is still okay for me to bid at $29,500, and the second person is still happy to pay for more price for car B, and he would just increase the maximum amount, which is $30,000. Right? Remember that this is the case when we assume that the agents are perfectly rational, they're intelligent enough to choose the most wisest decision for themselves. In real life, people would not do this, but we have the luxury as computer scientists to investigate this mechanism, because essentially the people who are drawn in this picture are agents that are artificially built as programs, that they're driven by programs. And we can actually specify these fixed rules for the agents to follow. Right? So at the end, the agent 1 and 2 will respectively get car A and car B, because no one wants to send out another bid. That I can summarize with an auction algorithm. So the algorithm, which I call a naive auction, would be functioned as follows. We initialize S to be an empty assignment, so there's no one has been assigned yet, and then we initialize a vector for price. So for every item, I initialize a 0 price for the item, and then I go into this loop, and essentially each repeat of the loop is a round of bidding, right? And basically you take an unassigned agent, so this would be an agent who's currently not holding any item in the auction, and the agent needs to evaluate and make a decision on whether to send out another bid, or if so, then which item to bid and how much. And to do that, he looks for the value of V minus P, so that's the current utility from every item, and he takes a maximum among of these values among all of the items. So now this X will be the item which gives agent I the maximum utility, right? And he will need to make a bid on this item. This is the procedure, so we just take the utility for this item to agent I, so VAIX minus PX, subtracted by the maximum utility from any other item. So the max among all of the X prime, which is different from X, and the corresponding utility VAIX prime minus PX prime, right? And that's our delta, and that's the price increase that we want to impose on item X. And then we add delta to the price of X, and this means that the agent AI has sent out this bid for this item X, and therefore he acquires this item through S. So we add the assignment from AI to X to the solution S. And also, if there is another pair where you already assign X to some other agents, and this person need to be released from this item, because this I prime person is no longer the holder of this item, right? And we repeat this loop until we have an unassigned item, or we have some agent who have not been assigned any item, right? Because the number of items and the number of agents are the same. So eventually we want to see every agent holding at least, holding exactly one item, right? And at that moment we stop. So that is the auction that I just described. It is quite straightforward to prove that when this algorithm terminates, the final solution that we get, which is the allocation from agents to items, would be an optimal solution. So we just need to show that it will be a competitive equilibrium, and because of the competitive equilibrium is necessarily optimal, so that final solution is an optimal solution. How do we do that? Well, note that upon termination, every agent has assigned an item as A, right? So we take A, which is an arbitrary agent, and we take the corresponding item that he gets at the end, which is X, and then we consider the last bidding step when A had made a bid on X, right? This is the time when A actually acquired X, and no one else would challenge A afterwards. So after incrementing the price of the item X by the corresponding value specified by the algorithm, X will still give a maximum utility out of all items. This is precisely because how we designed the mechanism to be, right? So in other words, after the price increase, X is still the best item from the perspective of A, right? And then if you look at all the subsequent bidding steps, they all involve other agents bidding on other items, right? So essentially X did not change, and when other agents bid on other items, this necessarily increase the price of the other item, and this means that the utility that A will get from the other item will just get lower and lower. It will never be higher than the utility that X gives to A. So this means that when the auction is ended, X is going to be the best item for A, right? And this holds for arbitrary agents, and therefore at the end, the solution S will give everybody their favorite item according to the current price. So that means it is in competitive equilibrium, and therefore the solution S is an optimal solution, right? So that's very good. The only catch is that the theorem holds only when we assume that the naive auction algorithm actually terminates, right? Is it possible for the algorithm to not terminate? Well, this is something that we have to check, and in fact, according to the current formulation, the algorithm may not terminate at all. Just imagine a scenario. Of course, it will not be a realistic scenario, but it's possible to occur in real life. For example, all the agents have the same evaluation, 110 of the three cars, A, B, and C. Then, if you run the algorithm repeatedly for A, B, and C, there are sometimes when we do not have any price increment to an item's price, because both A and B will give exactly the same local reward. And if you run this algorithm, you will see that the price increment delta after a while gets 0. And when delta is 0, you do not increment the price, and the auction basically stuck there, right? So this is the difference between the algorithm, the algorithmic auction, and the real-life auction. Right? In real-life auction, people are sensible, but in this situation, strictly according to the mechanical procedure, the price of the cars will not increment at all, right? And the auction will continue forever because it never satisfies the terminating condition. So that's really bad news, but can we do something to mitigate it? This requires a slight modification to the procedure. You can see that the real problem occurs when the value of delta does not increment. And we can force it to increase at each bidding iteration by having this extra small but non-zero value epsilon. Right? So whenever we have an agent making a bid on a particular item, it calculates the same price increment. Of course, it may become zero, but what we do is we just manually add epsilon to the price increment so that whenever we have a bidding for an item, we make sure that the price of this item is at least epsilon higher than the previous round. Right? All the other steps of the auction does not change. And we have this alternative auction mechanism, which we call it the competitive equilibrium auction, or CE auction mechanism. Right? And because of this, the price will always increment, and the process will eventually terminate. So this is an illustration of exactly the same example, but with the epsilon being 0.2. And you can see that eventually the agent will reach a solution. But now the question is, because we have a slightly different bidding rule, whether the optimality conditions still hold for this type of auction. What about optimality? When we have epsilon bigger than 0, we make another definition. We say a solution and a price function P will satisfy epsilon competitive equilibrium when for each agent, the utility by receiving the item as indicated by the solution is at least it's not necessarily bigger than the utility from all the other items, but we can guarantee that is not lower by epsilon, right? So formally, U of A S A is bigger or equal to U of A x minus epsilon for any item x, which is different from SA, right? So under this, in this condition, we say that this is epsilon competitive equilibrium. You can see this is a weaker version of the original competitive equilibrium. So you can think of it as a sort of relaxation. The good news is that if we implement the auction, the CE auction algorithm with price increment by at least epsilon in each round, we can guarantee that at the end, the solution that we get is epsilon competitive equilibrium. Right? So this means that the total reward of the solution is within epsilon times V of the optimal solution, or V is the number of agents in this setting, right? And does that mean it's necessarily bad? Well, in certain cases it's not, right? Because first of all, for the CE auction algorithm, when it terminates the final solution, we can guarantee that it's within epsilon V from an optimal solution of the assignment problem. But also, suppose now the reward function, the local reward function, maps every pair of agent and item to an integer rather than just an arbitrary real number. So suppose the reward function are integer values, then if we pick a small enough epsilon, we can guarantee that the result will be an optimal solution, right? And namely, if epsilon is less than 1 over V, you can see that it guarantees to terminate and find an optimal solution. And furthermore, we can also bound the number of bidding steps, which is V times the maximum amount AX is of all of the VAX divided by epsilon. Right? So that finishes today's lecture. We've discussed assignment problem from an economic paradigm. We've looked at multi-agent system in the form of a market to solve this optimization problem. And then we introduced this notion of competitive equilibrium. And then we analyze the auction mechanism that reaches a competitive equilibrium. Right? So that finishes today's lecture.